Hello everyone. I'd like to now finally talk about the rigorous way to compute derivatives of loss functions with respect to all the parameters in a neural network. Now first, I'm going to start with a pretty simple neural network with just one dimension. One neuron at each layer and one input and one output. So the input to the whole network is going to be one-dimensional. So I'll call this X. And each neuron is just going to have a single weight and a single bias. So I'll call this first weight W1, the first bias B1. And so the output of this, which I will call A1 actually. So I'll say A1 is equal to W1 times X plus B1. And that is what's going to come directly out of the affine part, or the linear part plus this offset. But then remember, what happens is this gets sent through a nonlinear function, which maybe I'll say the nonlinear function here is f1. So I'll put that in there. This could be something like a sigmoid or a leaky Rayleigh, or anything like that. So I'll say here that h1 is equal to f1 a1. All right, so H1 is what actually comes out of this first layer. And that goes ahead into the next layer. That becomes the input of the next layer. So H1 comes out. And actually then there's a weight, I'll call it W2, that H1 gets multiplied by. And then there's a bias coming into that layer. So I'll call that B2. And there's some nonlinearity that happens there. I'll call it F2. And so the output of this layer, first we're going to do the affine part, or the linear part plus the offset. So that would be W2 times H1 plus B2. And then we're going to have H2 equals F2 A2. All right, so then this outputs something called H2, and let me do one more layer here. And I think that'll be enough to illustrate what I'm trying to show. So the output of this is H2. That is going to go into another layer. We're going to apply a weight on the way in. So I'll call this W3, weight on the way into layer 3. Again, there's going to be a bias. I'll call this B3. And so the result out of that layer is going to be exactly like this, except it's going to be now, we'll say A3 equals W3 times H2 plus B3. And then H3 is then just the nonlinear function F3 applied to A3. So hopefully you see that pattern now. So out of this, we're going to have H3. And actually, I'm going to have a special name for H3 because it's actually at the end of my network here. I'll call this Y out. So this is, or maybe Y est is what I've been calling it elsewhere in code. This is the estimate that my network is going to give here. All right. Yeah, and let me remind myself that, yes, the final nonlinear function here is going to be F3. Okay. So I've got, my input is X, my output is H3 or Y estimate here. There's one more thing I'm going to do, actually, which is I'm going to compare the output with maybe the ground truth Y. So maybe I'll say, I have what my Y is supposed to be. This is called the ground truth, or the label I know my data is supposed to have. And I want that to be I want Y estimate to be as close to that as possible. So what I'm going to do is have a loss function. So here's my loss function, which is a function of Y and Y est. And this is something that I want to minimize at the end. So my h3 or my y_est is going to come out here. So, and then we're also going to input what the true thing is actually supposed to be. And we're going to compare, the loss function is going to compare those two, compute a number, and our goal is to minimize the loss function. All right, so our goal is to minimize L. Okay, that got a little bit cut off there. There we go. Good. So here is a neural network with 3 layers. It's kind of the simplest neural network with 3 layers I could possibly imagine, because each input and each output only has 1 dimension. So there's only 1 neuron in each layer. All right, so if my goal is to minimize L, I have to take the derivative of L with respect to my learnable parameters. And so those are the parameters that I can actually vary here, which would be the weights and the biases of each neuron, or each perceptron there. And so I need to know the derivatives of L with respect to those. And before I showed you how to estimate those in kind of a lazy way, but now I'm going to show you actually analytically how to compute the derivatives of the loss function with respect to this, recognizing all the elements of the function composition here to start you from the input x all the way out to the output y. All right? So first, let me start at the end. This is actually what we have to do when we have a composition of functions. We start with the outermost function first. So if I look at the derivative of the loss function with respect to h3, which that was the end of the chain here, starting with my input x all the way to the end. So if I look at just the last output from the network and vary that, I can ask, what is the derivative? Well, I mean, this depends on what the loss actually is, but let's say, for example, that we had this, we were using the squared loss that I showed before when I was doing it the lazy way. So here the loss function would be between y and h3, which is the same as y estimate. I just wanted to make clear that they were the same. That loss is going to be the square of the difference between y and h3. And so if I look at the derivative there, that is using our favorite power rule. So the derivative there evaluated at h3 is going to be, just by the power rule, 2 times y minus h3, right? Okay, so that's an example there, but I showed you other losses, of course, like logistic loss, and so depending on what the loss function is, you would have an expression for the derivative of the loss function with respect to what went into it. Okay, so let me go one deeper into the network now. So I know how the loss varies with respect to h3, but h3 is actually a function of this variable a3 here. Now, I'm not quite at the learnable parameters yet, but I'm almost there to a direct function of the learnable parameters. So let me figure out the derivative of the loss function with respect to a3. Now, I'm using Leibniz notation here to make this a little bit clearer. So what I can see is actually, if I want the derivative of the loss function with respect to a3, that is equal to the derivative of the loss function with respect to h3 times the derivative of h3 with respect to a3. And so this is the chain rule of calculus. And so what it's saying is, okay, the loss function depends on a3 through h3. So I have to pass through this function to get from a3 to h3, and then I pass from h3 to the loss. So the chain rule works that from the outside in. And the Leibniz notation here makes it very clear, because it's almost, you look at it like this and say, okay, it's the rate of change of L with respect to h3 times the rate of change of h3 with respect to a3. And if you look at it like this, it's almost like these cancel out and give you that equation that you want. So that's just the chain rule of calculus. And it's nothing to be afraid of. It's just the product of two rates of change, the outer one times the inner one. And so as an example here, let's suppose maybe that we had the logistic function. So let's say that, just to remind us, the logistic function of u is, that would be 1 over the quantity 1 plus e to the negative u. And so actually here that we're going to do logistic function of a3. So I'm saying here, suppose that suppose that f3 of A3 is the logistic function of A3. And so we can look at, okay, well, what would that look like then? In that case, the derivative of H3 with respect to A3, it's actually turns out to be quite a nice expression. That would be, if you recall, that would be the logistic function of A3 times 1 minus the logistic function of A3. So let me write that out here. All right, so that's just an example there. And so then you would plug that in, and you would get the entire derivative of L with respect to A3 as whatever this was, dl dh3 times this. Okay, so now we've gone all the way back to H3, and then actually to A3, and we're ready to go one step further now, and finally to one of the learnable parameters that we actually care about. So if I look here and I say, okay, now I actually know enough to compute the derivative of the loss function with respect to either my weight or my bias. So let me do the weight first. So let's say I wanted the derivative of my loss function with respect to weight 3. Okay, well, I notice actually the loss function depends on the weight 3 through A3. Okay, so luckily I know the derivative with respect to A3. And so I'm going to use the chain rule again. And I'm going to say, okay, the derivative of L with respect to W3 is the derivative of L with respect to A3 times the derivative of A3 with respect to W3. Now, because of the form of the perceptron here, this is going to be the same no matter what choice I make for the function or anything. Here, it's always the same function. It's always weight 3 times the input plus bias 3. So if I look at this, I can simplify it straight up, and I can say, okay, well, that's dl dA3 times, so the derivative of A3 with respect to W3, this is just a line. And so W3 is the only thing that's varying here. B3 is a constant when I'm considering this derivative. And so it's just the W3 that varies times a constant H2. So that turns out actually just to be H2. All right. So that's going to be H2 times the derivative of L times A3. Or sorry, the derivative of L with respect to A3. Okay, so that's the derivative of the weight there. And I mean, you could expand this even more if you wanted to, because we know, I could actually plug this in for dl dA3. I could make this expression look even worse than it is by just plugging in this whole thing for dl dA3. But I find it easier to imagine, it's like I'm storing intermediate results here, and I have this intermediate result of dl dA3. And I'm just going to plug in whatever I figured out that was. All right? So that's the derivative of L with respect to W3. So it's just the derivative of L with respect to A3 times H2, where H2 is the input. So you would have, in order to do this, you would have had to do a forward pass through the network, where you compute and remember all these H's and all these A's. But then you can use them here and plug them in on the way back. So you do a forward pass, and now you start to do a backward pass where you compute these derivatives, and then you can use the intermediate results and plug them in. So the derivation of the derivative for the bias here is quite similar. So I would say, okay, what's the derivative of L with respect to bias 3? So that would be derivative of L with respect to A3 times the derivative of A3 with respect to bias 3. And actually the derivative with respect to bias 3 is quite simple. Now I'm holding both of these constant. Bias 3 is the only thing that's varying, has a coefficient of 1. So it turns out, actually, that the derivative of L with respect to bias 3 is actually just the same thing as dl dA3. Okay? Okay, so I took a moment to rearrange some things here and to kind of cordon off what we've already done. We now know the derivative of the loss with respect to B3 and W3. That's great. Let's go a little bit deeper into the network now and try to figure out the derivative of the loss with respect to the second weight and the second bias. We're going to have to work from the outside in again. And so I see the first parameter on the outside there that then feeds into the next part is H2. So I'm going to need to know the derivative of the loss with respect to H2. So I look at that and I say, okay, well the loss depends on H2 through A3. Okay, so A3 is weight 3 times H2 plus B3. So that's where H2 shows up next in this composition of functions here. So the derivative of the loss with respect to H2 is, because it depends on L through A3, it's the derivative of the loss with respect to A3 times the derivative of A3 with respect to H2. Okay, so H2 depends on the loss through A3. Now I look at that. Okay, the derivative of A3 with respect to H2. That again is a nice just linear equation. And so I take the derivative treating B3 as a constant, because the only thing here that's varying is H2. And so then the rate of change is just W3, so just that constant in front of H2. So I can simplify this to, that's just dl dA3 times W3. All right. So now I know what the derivative of the loss function is with respect to H2. It's just the derivative of the loss function with respect to A3 times W3. And we already know the derivative of the loss function with respect to A3. You know, I had that written down here. So just store that intermediate computation, plug it in, multiply by W3. Great. Okay, so if I go one deeper now, then I actually want to know the derivative of the loss function with respect to A2, because H2 is a function of A2 directly. So now I want to know what dl dA2 is. Well, just like before, what dl dA3 depended on A3 through H3, we're going to say here that, okay, the derivative of the loss depends on A2 through H2. So A2 passes through H2. So I need to know what's the derivative of the loss with respect to H2, and then I can look at the derivative of H2 with respect to A2. So this is now we're starting to repeat the patterns that we had before. And that'll give me the loss there. So, and this just depends on, again, this depends on my choice of the function. So I'm going to leave it open for now. It just depends on what F2 is. So whatever F2 is, you know, if it's the logistic function, it would look like that again. If it's the leaky ReLU, it would look a little bit different. Okay, fine. And so now it's really just following these patterns. So if I want to look at the derivative of the loss with respect, ooh, I didn't have quite enough space there. Okay, I'll move this over a little bit. Yeah, so now if I want to look at the derivatives of the loss with respect to the weight, now I'm just doing some copy pasta. So derivative of the loss with respect to weight 2, well, the weight 2 depends, the loss function depends on weight 2 through A2. Oops. So let me just, I'll just overwrite these all real quick. All right, so here it is. So let's follow one example all the way through. I want to know how my learnable parameter W2 impacts the loss. So the derivative of the loss with respect to W2. Well, that's H1 times the derivative of the loss with respect to A2. Well, okay, so H1 is something I got from the forward pass. So first I do the forward pass, I remember all the H's, I remember all the A's. So I got that. So I plug in the H1, but now I need to know what's the derivative of loss with respect to A2. Well, that's something I computed before, and it's up here. Okay, that depends on what this function here is, so that's that term. And it also depends on the derivative of L with respect to H2. Okay, well that's something I computed here. The derivative of L with respect to H2 is the derivative of L with respect to A3 times W3. Derivative of L with respect to A3 is something that I computed over here. That depends on the derivative of L with respect to H3 times that function there. Okay, what's the derivative of L with respect to H3? So we, as long as we computed this stuff ahead of time, we can remember these intermediate results and then plug them in. So this is why, again, why we call it backpropagation. You start from the end of the function, or if you're going to write this down as function, to be the innermost part of the function, or sorry, the outermost part of the function. So the end of the function. And we're going to slowly work inwards to the left. And this is what we get. And so now we sort of fully specified the pattern that's going to continue. I could go now as deep as I wanted. Let me just copy and paste this and do the proper substitutions. Okay, so here it is in its full glory. And just, you know, you can check me at every stage here. I'm doing the chain rule. In Leibniz notation, I think it's quite clear. I want the derivative of something with respect to a variable. I look and see what is the direct thing that variable influences. So in this case, W1 directly influences A1. So I need to do the derivative with respect to that first, and then I can do the derivative of the inner. And I get what I'm looking for. Whoops, I forgot to do a substitution there. There we go. That's the danger with copy-paste. You got to be careful about that, both in math and in code. Okay, yeah, so anyway, I should be able to check here and see that the chain rule is making sense for everything that I look for here. And we're just, this is a composition of many functions, so we go very, very deep. That's why it's called deep learning. And so we just have to make sure that, you know, we work from the outside in. So chain rule always starts at the outer and then works in. So we'll remember the derivatives of the outer things, and we'll be able to plug those in successively to deeper and deeper things on the inside until eventually we get down to the parameters at the very beginning. So, and actually there is one little tweak, I guess there's one little tweak I have to do when I get to the very beginning. The derivative of A1 with respect to W1 here is actually, this should have been, instead of H1, this should be X. Okay. So the derivative of A1 with respect to W1 is X. That's kind of a special case. Once we get all the way back to the beginning, finally you see where the input starts to influence things. So the input's going to flow through here and go there. Okay. So I could have called maybe the input, to be consistent with my notation, I could have called the input maybe H0. And then all the, you know, then the indices all kind of line up. Okay, but so just to show you, TensorFlow's playground kind of depicts backpropagation in a certain way. So, you know, it shows us here that you know, the forward stuff is flowing here, but then actually backpropagation flows back through these lines from the loss at the output back to the beginning. Okay? So that's really, that kind of pattern is all there is to backpropagation. Now, it's true that this is a bit of a simple example, but the general pattern is the same. We always work from the outside in. So we do a forward pass and then we work from backwards. And then if we do that, we always have everything that we need to plug in to determine the derivatives with respect to inner parameters. All right, so these expressions down here are all the ones that I'm ultimately interested in, because these are the derivatives with respect to my learnable parameters. I do have to compute some intermediate stuff to help me. So derivatives with respect to the output of the each neuron I need. I also need the derivatives with respect to the linear part, or the affine part, the weight plus the bias before they're composed with a nonlinear function. So these are kind of intermediate things I need, and they'll help me to get what I'm ultimately after. So it's helpful if I remember all the A's and the H's as I'm going through. So what you're going to do in an assignment is generalize this to multi-layer perceptrons, where actually you have more than just one neuron in each layer, and these neurons all feed into each other. And so in that case, it really is very much the same idea, but instead of these kind of just scalar multiplications here, there's going to be some matrix multiplications. But otherwise, it's really kind of the same idea. I'm also going to have you watch a video from Andrzej Karpathy. He does a very nice job of showing how to make a more general purpose. He calls it micrograd. So he's going to do the same thing, working from the back to forward, but But he shows what happens if, this is very structured. And the multi-layer perceptron is very structured. He's going to show you what to do if you decide to not have something so structured. So, this is not the topology of how the neurons are connected might be a little bit more complicated. So he'll show how to deal with that. So I'll have you watch that. All right, but this is the intro to backprop. So you just gotta get your chain rule, and that's it. So backpropagation, just a fancy name, fancy branding for the chain rule in the context of training neural networks. So finding the derivatives so that we can then do gradient descent and find parameters that better fit our data.